this one. All right.
Hooray! All right, guys, welcome to our LINDIF review night. I know that says night 3. It's actually night 2. You didn't miss one. Don't worry about it. So we'll be going through examples today, mostly the applications. If you have any questions throughout, please raise your hand. And then there'll be a couple times where you guys can work things out on your own. Please feel free to raise your hand, ask any questions. We'll be wandering around. But yeah, with that, let's get started. Is this the empty slides?
I think so.
Yeah, so that's an empty, this is a version of the PowerPoint with the questions, but not the answers. So if you want to like scan the QR code, download it to use as your notes, you can. Yeah, I'll leave that up for a few seconds. Go crazy. Sweet. Okay. Also, just so you guys know, we're recording this, but it's just recording the screen. So you guys aren't being recorded. And then they're going to put that up on YouTube probably soon. We'll see.
The one from last night got uploaded this week.
It does? Okay.
Happy to work with that.
Yeah, sorry about that. Okay, turtles. Woohoo! Except actually it's about warthogs. Woohoo! Okay. So this is our problem. We've got this Warthogs College established in 1127 by introducing 91 wizards. Oh wait, I gotta turn on my colors. Yeah. Yeah. Introducing 91 wizards. So that's going to be our initial conditions, right? For the problem to the academy. Faculty advance discreetly according to the following promotion rates. So we're going to use these promotion rates to determine our matrix of how people are moving through this system throughout the years. And then it wants us to eventually determine how many faculty are currently at Warthogs. So if it was started in 1127 and it's currently 2025, then that difference is a really big number. So we're kind of essentially taking the limit as it goes to infinity. But we can calculate it actually if we want to. So setting up this matrix, we will want, I'm going to set up, how I like to set my variables is S, C, and F for assistant professors, associate professors, and full professors. That's so confusing, and I'm probably going to mess up my words, but we're just going to roll with it. And then when I set these up, I like to write it across the top to remind myself like what relationship I'm looking at. So it says, Warthogs maintains the same number of assistant professors each year. So what that means is this first row right here, that's going to all add up to equal my assistant professors at the end. My second row will give me my associate professors. Third row will give me full. So I'm going to go, okay, all of my assistant professors, which is going to be in this column, are going to stay in this row. So that means I'm just going to leave a 1 here, okay? That's how I think through these. And then how many associate professors are going to become assistant professors? 0, right? And how many full professors are going to become assistant professors? Also 0. No one's getting demoted. So that's really good. And so next, we're given 16% of assistant professors become associate professors each year. So that means I'm looking at the relationship between my associate professors, which is this row, and my assistant professors, which is this column, right? So I'm looking at that position. If 0.16% of them are moving on, that means that I'm going to put a 0.16 right here. So that when I do my multiplication, 0.16 of my assistant professors are getting added to my associate professors, right? And then moving on to our next line, 8% of associate professors become full professors every year. Okay, so I'm looking at how my associate professors, which is going to be in this column, relate to my full professors, which is in this row. So I'm looking at this part right here. And if 8% of them become full professors, that means I'm going to put a 0.08 right here, so that when I do my multiplication, it adds. But if 8% of them move on to become full professors, that means that 92% of them have to stay as associate professors, right? So that means I'm going to put a 0.92 right here. So when I do my multiplication, that 0.92 stays. Okay. And then filling out this row right here, how many full professors get demoted and become associate professors? Maybe they should, who knows? But and then how many assistant professors get promoted to full professors all at once? 0, right? They have to move through and become associate professors first. And then it says 4% of full professors retire each year, which means that 96% of them stay, right? So I'm going to put a 0.96 right here. Okay, so now we have our matrix. Hooray! All right, so if this is our A matrix, we are trying to find A will be to some number n times our U naught to equal our U at some number n, where n is going to be some big thing, right? So the first thing that I want to find is my eigenvalues. Now, thankfully, this is a lower triangular matrix, which means that my eigenvalues, lower triangular because all these are 0, so my eigenvalues are just going to be along the diagonal of my matrix. And when we write our eigenvalues and eigenvectors, we always order them from greatest magnitude to least magnitude. So my eigenvectors are going to be 1, 0.96, and 0.92, right? Awesome. Okay, so now I need to find my eigenvectors. So fun. To find my eigenvectors, I take my original A matrix and then subtract my eigenvalues off the diagonal. So in this case, I'm going to subtract 1 off of the diagonal. So this first row is going to be 0, 0, 0. This 0.16 stays the same. And then 0.92 minus 1 is negative 0.08. Ugh. I'll move things over. And then that 0 stays the same. And then that 0 stays the same. 0.08 stays the same. And then 0.96 minus 1 is negative 0.04, right? And then that multiplied by my first eigenvector is going to give us 0, 0, 0, is what we need to find. Now this step, you could go through and like find the null space, do a bunch of fun things, but how I usually like to solve these is by looking and saying, okay, if this was a system of equations, right, I'm going to pin down one of them as being 1 so I can decide on the rest of them. So I'm going to choose my one that's associated to the greatest value, so my first one to be 1. Why not? And then if this is multiplied by 1, meaning it stays as 0.16, what do I have to multiply this one by so that when they add together they equal 0? 2, right? So now that's 2. So then if this is 2, if this is 2 times 0.08, making it 0.16, what do I have to multiply this by so that we get 0 when they're added together? 4. Right. Okay, perfect. So that's our first eigenvector. Now, moving on to our second eigenvector, we're going to subtract 0.96 off of the diagonal. So 1 minus 0.96 is 0.04, and then 0, 0, 0.16. 0.92 minus 0.96 is negative 0.04, 0, 0, 0.08, and then 0. Now we're looking for eigenvector number 2, all equal to 0. Okay, perfect. So now looking at this one, looking at this very first equation, what do we have to multiply this 0.04 by to get 0 in the end. 0, right? There's no other way that we're going to get 0 in that row. And then looking at my third row, what do I have to multiply that 0.08 by? 0, right? So then, or sorry, I put that in the wrong spot. 0. Now this is a kind of a trickier one. These are both 0, but what can I multiply this by and still get 0? Literally anything, right? Literally anything. But I'm going to choose 1 because it makes my numbers easier. Okay, so eigenvector number 2 is going to be 0, 0, 1. Now, looking at eigenvector number 3, I'm going to do it over here. Sorry, team. We're going to be a little disorganized, but we're going to work on it. So I'm going to subtract 0.92 off the diagonal. So we get 0.08, 0, 0, 0.16, 0.92, that's going to be 0, 0, 0, 0.08, and then 0.04. Yeah? Multiplied by V3 to get 0. Awesome. Okay. Then my V3, I'm going to reorganize this in a second. What do I have to multiply this first column by? 0. Awesome. And then on this second column, I mean these second two, the relationship here, right? This third column is half of the second column. So I'm going to, I know that one of them has to be negative. And I'm going to, because I want to deal with whole numbers, I'm going to put a -2 in my third one and a 1 in my second one. And I can always check my math by multiplying across and getting 0.08 and 0.04 times -2, which is -0.08 equals 0. Yeah? Okay, awesome. So then this means that my eigenvector matrix is going to be 1, 2, 4, 0, 0, 1, 0, 1, -2. Awesome. I'm going to erase these. Yes.
Okay, I'm sorry. I know how to do this. I know how to do this, but I'm just getting stuck up. Can you
Sure.
explain how to get the V2? Like why those two are 0?
Yeah, for sure. So looking back at V2, over here. Oh my gosh. Wow, that was really awesome. This is 0. Okay. The only way I'm going to get 0 in this equation, right, is if this 0.04 is multiplied by 0, right? Okay. And then the only way I'm going to get 0 in this equation is if 0.08 is multiplied by 0, right?
Oh, okay, you're going.
Yeah, I go by columns. But each of these rows is kind of like its own individual system of equations. You can think of it that way. Where, like, in a way that's more familiar, this would be multiplied by x, this would be multiplied by y, this would be multiplied by z. All of that has to equal 0. And then we can solve for x, y, and z. That's how you would solve this like a system of equations. But a matrix is just a more consolidated form of that. Does that make sense? Yeah. It would if we were just, yeah, because you're also multiplying it by 2. So because we've already established that our second column is being multiplied by 2 because of a previous one, now this becomes 0.16 minus 0.04 times some like x something has to equal 0. So then we just solve that over and we get 4. Does that track? Okay, awesome. Perfect, perfect, perfect. Okay. Any more questions about how I got my eigenvectors? Okay, then I'm going to erase them just so we can have some more space. Okay, perfect. Now that I have my eigenvector matrix, I know that in my diagonalization formula, I need to have the inverse, right? But here's a fun thing that I'm going to do. As we go to a super high number, I know we're not going exactly to infinity, but we're going to a really high number, right? What's going to happen to the matrices associated with these two values? They're basically zero, right? So that means that really all I'm looking for is my first eigenvalue, which I already have, and my first row of my eigenvector, which I already have. First column of my eigenvector matrix, which I already have, and my first row of my eigenvector inverse matrix, right? So in reality, if we can get the first row of our inverse eigenvector matrix, we don't really need the rest of it, right? We can calculate it, but we don't have to. So I'm probably not gonna. So how I usually get the inverse of a 3 by 3, I set it up. So 1, 2, 4, 0, 0, 1, 0, 1, negative 2. That's my eigenvector matrix. And then we augment it with an identity matrix, right? And then I am going to make do reduced row stuff to this matrix until it looks like this matrix. And then whatever I get on this side is going to be my inverse, right? But again, I only really care about the first row. And when we look at our first row of this matrix, is it any different than the first row of this one? No. Meaning that as I put this in reduced row echelon form and change it to look like the identity, this first row isn't going to change, which means that I already did the first row and I'm done. So that's pretty awesome. Sweet. So I can set up now as that A, as it goes to infinity, is going to be equal to my first eigenvalue to infinity, which is just 1, which as it goes to infinity is also just 1, which is super awesome, multiplied by the first column of my eigenvector matrix, which is 1, 2, 4, and then multiplied by the first row of my inverse, which is just 1, 0, 0. And then all of that is also multiplied by my initial conditions, which in this case is 91, 0, 0. I assume that all of the 91 wizards are going to start as assistant professors, that they all start their lives as assistant professors. I don't think that's really stated, but that's an assumption we have to make. Okay, so now I just need to do some funky little multiplication. I'm going to start with this one because it makes my life easy. When I multiply these two, I'm going to get a 1 by 1. I'm going to get a scalar. So 91 times 1 is 91, and then 0 times 0, 0, 0 times 0, 0. Boom. Awesome. So now I'm looking for 1, 2, 4 multiplied by 91, which will equal 91, 182. Someone have 91 times 4?
364.
364. Awesome. So as we go to infinity, this is the distribution of our professors, meaning that there's going to be 91 assistant professors, 182 associate, and 364 full professors. So then to get the total number of professors, we just need to add all those together. So 91 plus 182 plus 364, which equals, does someone have it? 637. Do you just have this memorized? Oh, yeah, this is so true. Yeah, okay, so that's our final answer. Do you guys have any questions about how all that was done? Anything at all? We feel pretty good? Yeah.
Quickly go over again what the rank matrix.
Sorry, say that again?
The dominant eigenvalue is making a rank matrix out of it.
Yeah, that is what we're doing. Yeah. We're taking our original A and we're separating it into 3 rank 1 matrices, and then saying that as we go to infinity, these two are gonna not matter anymore. And so I'm only focusing on the dominant rank 1 matrix. Yeah? So we never calculated the full inverse matrix. Because we said I only need the first row of the inverse matrix, and the first row is going to be equal to that, to 1, 0, 0. Do you understand why? Yeah. Exactly. Exactly.
You only take the first eigen.
So. Yeah.
Hey, can we kind of quiet it down? We're trying to answer a question. It's getting a little bit hard to hear. Thank you.
Thank you, Carson. Okay.
This is, and then that's just a rank 1.
Yeah. Uh-huh. Yep.
Then what's the last column?
The last column, these are our initial conditions. Those are our initial conditions.
All of that comes from.
Problem statement. It says it established at this year introducing 91 wizards.
And that's just the amount
Yeah.
of assistants, right? We're looking.
Yeah, we make the assumption that they all start as assistants,
Okay.
which isn't real, but that's fine.
And that's gonna be all for it.
Yeah.
Okay.
Sweet.
And then the 1 to infinity is.
It's just 1. 1 is my first eigenvalue, my dominant eigenvalue.
Got it.
Yep.
Sweet.
Okay, no problem. All right. Don't worry about it. Ooh. What? Okay, yeah, that's all the work I already did. Awesome. Oh, I guess it has the answer already on there. Awesome. Okay, this is turtles number 2. This question, I made it, like, when I took this class, I made it so complicated. And when I saw the answer on these slides, I was kind of upset. I'm not gonna lie to you. Okay, so we're back at warthogs. But they have found through studies or whatever that they, how many students transition from like freshman to sophomore to junior to senior, etc. Through it. So pretend you can't already see the matrix. If warthogs admits the same number of incoming freshmen each year, then this 1 has to stay constant, right? That means that we're going to have the same number of freshmen every single year as we already started with. And then if 60% of freshmen become sophomores each year, 60% is equal to 3/5. Yeah, 0.6 over 10. Anyway, is equal to 3/5. So if 60% of freshmen become sophomores, where am I going to put that 3/5 without looking at it? We're going to put it right here, right? Because this is the intersection between my freshmen and my sophomores. Freshman column, sophomore row. Yeah? So then if 3/5, okay. No, I have to do this. And then 3/5 of sophomores become juniors too, right? So that means I'm going to put my 3/5 right here as well. That's my number because this is my sophomore column, and this is my junior row. So that's my intersection. Okay. But then if 3/5 of sophomores become juniors, then that means that 2/5 of them stay as freshmen, right? I mean, sorry, as sophomores. 2/5 of them stay as sophomores if 3/5 of them become juniors. Okay, awesome. And then if 3/5 of juniors become seniors, it's going to be the same story. I'm going to put 3/5 right here because that's the intersection between my junior column and senior row. But then if 3/5 of them move on, that means that 2/5 of them have to stay behind, right? Awesome. And then if 33% of seniors graduate, okay, 33% of them are moving on, 1/3. 1/3 of them move on, which means 2/3 of them stay behind, right? So I'm going to put 2/3 right here. And then the rest of it, spoiler alert, I fill out with zeros because this is the only movement that I have in my system is what's already been specified. Okay? So this whole thing though has been kind of our units are students per year, right? But this is asking about years per student, right? So I am just going to take the reciprocal of all of these rates so that now my matrix is in years per student instead of students per year. Okay? And then, so we get,
Decimals, the fraction.
I think fractions. Yeah, I think fractions. Yeah. I think it's fractions, especially because we have to take the reciprocal. So then, like, taking the reciprocal of fractions is way easier. So then, since these numbers are the amount, if I take the reciprocal of them, these numbers will give me how many years it takes on average to move to the next time step, right? So then that means that my average number in total of years it'll take to graduate to move through the entire system will be the sum of all of those numbers. So I'm going to sum the reciprocal of all of them. So 1 plus 5 halves plus another 5 halves plus 3 halves. No,
Why is it the reciprocal?
no, I lied. Why is it the reciprocal? Because we started in students per year and we're moving for years to students. I think that my thing is messy. I think that's why. It's because we're looking at these values. And then the 1/3 value. Like that. And not that one. Okay. So I'm just taking, honestly, I don't think in this problem, I don't think that the matrix itself is super duper helpful, TBH. I usually just write these on the side right here. Take the reciprocal of all of these. So we get 5/3 plus 5/3 plus 5/3 plus 3. And that equals 8. Does that make sense? I know I messed up there. That's my bad. Honestly, I wouldn't even set up a matrix for this. I would just look at all of these. Yeah? Do you have a better explanation? Okay.
I think that setting up the matrix can be helpful because these spots underneath show the progression. And what we're concerned about is how many years it takes students to progress. So that's why you're not taking the diagonal values, but you're taking the values underneath the diagonals. So you take the values underneath the diagonals because that represents the progression of students. And you're wanting to find how many years on average it takes students to progress through graduation. Does that make sense? And that's why at the end, we don't take that 2/3 in the last position, but we take a 1/3. Because if this matrix were to say, like, let's say we had an extra row and column for students who graduated, we would have a 1/3 right there underneath it. Does that make sense?
Yeah. Thanks, Carson.
You're welcome.
Appreciate you. Okay, awesome. That was a little confusing. Do people have questions? Do we understand? Yes.
And 3 comes from.
3 comes from 1/3
And why do we take the reciprocals?
because all of these rates, the 3/5, 3/5, 3/5, 1/3, those are all in students per year. And we're trying to find years per student. Yeah. Okay. Awesome. Do we have any more questions? Okay. Cool, cool, cool. On to SRI, our favorite ever. Woohoo! Okay. So, all right. So we have this situation, okay, where we're looking at the movement of people who are susceptible, people who have recovered, and people who are infected with COVID-19, okay? And then we are given all of these conditions of how people move through our matrix, okay? We are also given coordinates, essentially, of where each of those things are going to be placed, but just going through how it would be set up. If the population is growing at 1%, that means that my entire population has to be multiplied by 1.01, right? Because it's growing at 1%. So it's what we already have plus 1% more. So it's 1.0, 1.01. Awesome. And then 2% of those who are recovered go to being susceptible. So that means that I'm going to put a 0.02 right there because that's my recovered adding to my susceptible. Those who recovered remain immune until they're susceptible again. This is just saying that if 0.02 of them become susceptible, then 98% of them, 0.98, are going to stay recovered. So we're going to put that right there. And then 7% of our infected become recovered. So that means that I'm going to put a 0.07 right here, right? Because then that's my infected adding on to my recovered. And then 5% of my susceptible become infected. So I'm going to go down here with my 0.05 because if I do my multiplication of SRI, then I get 0.05 times S added onto my I, which is what I want. And then 92% of my infected stay infected. That's going to be my bottom one right here and stay where they are. It says the infected who don't recover or stay infected die. Just super gruesome. But we're not tracking how many people die. So we're not that worried about it. Okay, so this is my matrix. And then what it is asking me for is the ratio of how many people, does it say, what percent of the population will always be sick over time? So eventually what I'm looking for is I over I plus S plus R as we go to infinity. Okay, awesome. So the first thing I need to do is find my eigenvalues. Now, I'm not going to go through the entirety of solving all these eigenvalues because it gets super duper nasty. But how you do it is you take 1.01 minus an eigenvalue, 0.02, 0, 0, 0.98, 0.07, 0.05, 0, and 0.92. Yeah, sorry, I forgot. That's my bad. Minus lambdas on all those. And then you take the determinant of this matrix and you set it equal to 0. And you're going to get a third order a third order polynomial, and you'll have to solve for 0, essentially. You'll get some lambda cubed plus all this other stuff, okay? And this is a problem that you need a calculator for. You can't do this without a calculator. I'm sorry. So I'm showing you conceptually how to work through it and how it ends up working because I don't want to waste people's time. Okay, awesome. And long story short, when you find your eigenvalues, you're going to get, sorry, moving over in my notes. You get about 1.03, and this is kind of scary, but it's fine, I promise. 0.94, I'm going to round here, 0.94 plus or minus 0.013i. It's fine, it's fine. Yeah, there is an I, but it's fine actually. If we think about what this means for our system, essentially what's happening, because both of these are very small and lower than 1, as we go to infinity, they're going to get super duper small, right? Meaning that as we get to infinity, our populations are all growing and they're still moving about in the system. Like people who are infected and recovered, it's still moving about in the system, but the effect that moving about is having is getting less and less and less as we go to infinity. Okay, so yeah. So we have some cycling, but in the end, it doesn't actually matter that much. Okay, awesome, awesome, awesome. Okay, so now we need to find our eigenvectors. But a nice thing about this is that because we are just looking for this ratio right here, let's step back and look at, ooh, I didn't want to do that. It's fine, actually. Let's step back. I'll rewrite it. How this diagonalization is going to work out. So A, as we go to infinity, is going to be equal to our eigenvalues to the infinity times V1 times the first row of V inverse multiplied by our initial conditions, right? Okay. And spoiler alert, because 1.03 is greater than 1, we're going to go to infinity. In other words, we're not going to get a singular value as we take this limit. That's why we're just looking for the ratio. And when I multiply these two vectors together, what shape do I get of a matrix? You're just going to get a 1 by 1, right? You're going to get a 1 by 1 that's some constant, right? And so then, because I'm multiplying this this eigenvector by some constant and also infinity, is that constant going to matter? Do we care what that constant is? No. I'm just looking for the ratio, so I don't care. In other words, we only need to find our first eigenvector and then we're done. So even though this is really scary, it doesn't actually matter. So that's really nice. Okay. All right. So then to find my first eigenvector, I'm going to set up my matrix. So I'm subtracting off 1.03 from my original A matrix. So 1.01 minus 1.03 is negative 0.02. 0.0200, 0.98 minus 1.03. My brain doesn't work. Who's got that? Negative 0.2. 0.05. That sounds more correct. 0.07, 0.05, 0. 0.92 minus 1.03. Who's got it? 0.09? I'm getting different answers. This is concerning. 0.92 minus 1.03? 1. Okay. I'm trusting you. I think that's what I have written down. Okay. Okay. All of this multiplied by my eigenvector matrix should give me 0. Okay. Because these aren't super nice numbers, I'm going to set this up as a system of equations. I'm going to erase this because it doesn't matter.
Impossible to solve.
So I'm going to start by setting one of them equal to 1, just because that makes my life easy, and then I can start putting it out. So I'm going to set my third one equal to 1. Sure. Okay. So then I get, looking at this bottom row, I'm looking at the bottom row right now, and I'm setting my third one equal to 1. So I get 0.05 times, I'm going to call this V1, minus 0.11 times 1, because I set that equal to my V3, is equal to 0. Okay, so then that means that my V1 has to be equal to, someone have it? It's like 0.02-ish. Okay, so then if I can then move to my first row, I'm looking at my first row, I'm going to have negative 0.02 times 0.02-ish plus 0.02 times V2 equals 0, which means that V2 is going to be equal to 1. No, -1, more or less. And then I've already established that V3 is equal to 1. Okay, perfect. So then that means that my eigenvector is equal to 0.02, -1, and 1. Okay, so then if I have this eigenvector, I know this eigenvector is going to be multiplied by some constant, it's going to go to infinity, but this is going to be the ratio, this is going to dictate the ratio of my final conditions. So I'm going to plug it into this formula. So I have my infected, which is more or less 1, divided by 1 plus 0.02 minus 1, and you get 1 divided by 0.02. That's basically what I did. More or less. I know I did some crazy rounding here, but the process, I think, is more important than the actual number. Does anyone have a number for that? Hmm? Did I do something wrong?
Your first
V1?
called like eigenvector.
Uh-huh.
You see how like on the top row it's negative 0.02 and then 0.02. So shouldn't your first and your second value be the same instead of?
Yeah.
Yeah, just the I.
Yeah, I messed up that math. That's my bad. Okay. I'm going to start over on this to make sure I did it right. Okay. Hey, that's my bad, gang. That's my bad.
So,
Okay. Because this is right, right? Yeah. Okay. Looking at this bottom row, I have 0.05 times V1 minus 0.11 is equal to 0. That's what it is. 2.2?
Yeah.
Yeah. I think that was wrong in my original. Okay. So then V1 is equal to 2.2. Yeah, that makes more sense. Which means that then when I plug it into here, now I'm looking at this equation. Yeah, now I'm looking at this equation. I get negative 0.02 times 2.2 plus 0.02 times V2, which means that V2 should be equal to 2.2. Yeah, 2.2. And V3 is equal to 1. That seems a lot more likely. That makes more sense. Okay. So that means that my final eigenvector, 2.2, 2.2, and 1, more or less, which means that my final ratio is going to be 1 over 1 plus 4.4. Yes.
My question is, we can't really satisfy all 3 rows of that matrix, because in order to satisfy the middle row, we'd have to do 1.4 in the middle for eigenvector.
So I think that comes from the fact that we've done some pretty wild rounding in here. To be honest, I think that's what this comes down to, right? Yeah, it's just a rounding error. Because all of these decimals, even my eigenvalues, are decimals that go on like 5 or 6. They go on for a long time. You know what I'm saying? So we have some error inherent in our system. Yeah. Okay. Do we have any other questions about this application? You feel pretty good about it? I'm gonna say that means yes. Awesome. Woo! Okay. I think that's it. Sweet. Go crazy. Yeah. Mike the guy.
Hello. Does that work? Does it work?
Yeah.
Oh, I see. Okay. Oh, that's sorry for everyone on Zoom. Okay. Hello, everyone. Today I'm going to teach you guys about regression. So regression's great because Carson.
Hey, let's settle down a little bit.
Thank you, Carson. All right, so if we have a bunch of data points and we need to fit them to like a line, but they don't fit all on the same line, then we use regression. And we can do this with matrices, and it's kind of cool. So I'm going to redraw this data. Actually, how do I erase? Do I just flip it around? Oh, that's so cool. Okay, so we have a bunch of points. I'm going to draw them out. And then the model, oh yeah, can I move this? Oh, cool. And that's the equation that it wants us to model, and these are the points that it's given us. And so we can plug these points in for x and for y. That's also y. And then we can use the equations that we get to make a system of equations to solve for a and b, which will give us the equation for the function that models it. So we can plug each point in for x and for y. So for this one, x is -1, so that would be negative a plus be to the -1 equals 0. And then 0 equals 0 plus b. Wait, for the first one, it's x. So this is the x term. Can you see my cursor when I do that? They can't see my cursor? Oh, so this is the x one right there. And so that gets plugged in for x here and x there. The y is 0 and the y goes here. So for the second one, yeah, because x is 0, it gets plugged in here. Can you guys see? You can't see? Oh yeah, you can. You can see my cursor. Okay. It gets plugged in, 0 gets plugged in here and here, so this just becomes 1. And that's b. Does that make sense, everybody? Okay. And this one is 0 on this side, a plus b e, and then 18 on this side, and then 8a plus b e squared. And so now we have a bunch of equations. I'm going to erase these. Now we have a bunch of equations, and we need to solve for a and b. So we can put these into matrice form. Oh, I did this kind of backwards. I'm going to put these over here so it makes more sense. So we're going to put this into matrice form. So this first column is going to represent the coefficients in front of our a. So this first one is -1, then 0, then 1, and then 8. And the second column is going to represent the coefficients in front of our b. So that's e to the -1, 1, e, and e squared. And then we'll multiply that by a and b. And then on the other side, we're going to have our y values. So 0, 0, 0, 18. And so normally, if we had like just two equations, we could just take the inverse of this and put it to the other side. But because it's not square, we can't take its inverse. So we're just going to make it square. And to do that, we're going to multiply it by the transpose. So the transpose of this matrix right here is -1, 0, 1, 8. E to the -1, 1, e squared. And then we're going to multiply this over right there too. And so we have to do some matrix multiplication, which is never fun. 1 plus 0 plus 1. Oh, it's just squared. So plus 64 for that first one, which is 66. And then negative e to the negative 1 plus 0 plus e plus 8e squared. So that just, yeah? Did I mess up? Do you want me to go slower? Okay. Oh, so you see how x is cubed right here? So when we plugged in 2 for x, it got cubed. Because we have all these data points which represents x values and y values, and we're just plugging them into our function to get equations. So like,
And we move that over to a matrix.
Yeah.
Coefficients.
yeah,
One by eight b, and then there we multiply it by the transpose. Right?
Yes.
On both sides.
yes.
Just checking why we had CME squared, but not, that makes sense, now, those are
Okay.
coefficients.
Yeah.
These like, he popped up.
Okay. Sorry. All right, and then this, I can erase that. This is kind of a nasty looking matrix right here. Okay. And then this would be the same thing down here. And then these two. Okay, does everyone understand where I got this matrix right here from? Yeah? Okay. Oh, sorry. Can I move stuff on this? How do I do that? Do I just, okay, I'll just do it. There we go. That worked.
And
Okay. Is everyone good for me to move on? You guys are still writing stuff down? I'll wait until I see people that look like they're not writing stuff down.
on the matrices, we've got coefficient. Right, transpose. Transpose, then it's y dot.
So this right here, this is like a, what is this second, what is the variable used for the second matrix over here?
Just some second.
X. And this is,
So that's also multiply that all through, that's what.
did I keep going? These guys are, I can't tell if they're just chatting or because they might be talking to figure stuff out. So I don't know. I don't want to interrupt them.
Are we ready to move on? Yes.
Okay, sweet. So then you'll do the same thing on the other side here. And that gives like, what is that? 0, 0, 0, 18 times 8. Someone have a calculator and want to find 18 times 8? Thank you. Okay, and then 18 e squared. Okay. Oh wait, this is supposed to be square. Yeah, this is square. Okay. So now I have a square matrix right here. It doesn't look square because it's really ugly, but it's square. And so now we're going to take the inverse of this one and multiply it by its inverse to get rid of it. And we'll have to do that to both sides. So we're going to do, if we call this A, we'll just do this A negative 1, or A inverse over here. And then we'll do that. Can I do that without a calculator? I can't do that with a calculator. Okay. Yeah. So A is this. This is A. Yeah. So does someone want to calculate A inverse for me? Okay. This is A transpose. Sorry.
A transpose.
Thank you. Oh wait, yeah. Wait, the whole solution. Oh, that's cool. Guys, you don't have to calculate it for me. I'll find it. Oh, does it go away? Well, I mean, my writing. Oh, I see. Okay. Wait, that's an. Oh,
Yeah, keep going.
yeah. Okay.
Keep
Okay.
going. Keep going. There's A transpose A. And there's the inverse.
Okay. Okay, I'm gonna ignore that. So we're here now, right? So we have on the left side, after we did A transpose A inverse times A transpose A, A transpose A inverse, A transpose A. So
Just A train.
on this last one, wait.
Yeah.
For
Yeah.
Oh, okay. Okay.
Great. He's favored.
Thank you. Okay, so these cancel out. Once we multiply this by both sides, these cancel out. And then we get x is equal to whatever these multiply out to be, which ends up being this. So this right here is the inverse of A transpose A. This was A times our y vector from all our y values. And when we multiply these together, we get these two values. And these values represent what we can plug in back to our original function, which was, what is that? F of x is equal to 2.3553x cubed plus, I actually don't remember it. Minus?
It's the numbers in there.
Okay, minus 0.186537 e to the x. Sweet. Does anybody have any questions? Yes, okay, you're first. Oh, I see. Yes, you're right, that is the y vector. Instead, what they did, sorry, I got this wrong. This is what that is. Yeah, thank you. But yeah, they did that. But when I was doing it, I multiplied these out first. But yeah, you're right. Okay, any other questions? Okay, yeah. Yeah, like you said, formatting it is kind of weird, but like the idea is pretty simple. Like it's just you're trying to find like something here, but this isn't square, so you just make it square by multiplying it by the transpose. And then if you just after you do that, if you just solve it the way you would any matrix, then you'll get your answer. Yes.
So if we multiply those values in, because it's a projection or whatever, when they plug our original values of A in, we won't actually get our values of Y out of this.
No.
The difference between those values is great.
Okay.
Wait, any more questions? Awesome. What? I think it's your turn. Oh.
Take it out of your pocket, please.
Oh, that's what one.
All right, everyone. Now we are doing circuits. And if you remember, circuits are a bit more straightforward than some of the other things we've been doing. If usually you are given an you're given a circuit system like we have over there in that picture on the left right here. Very fun. And those have different nodes and different paths. So if this was like your electronics class, those are your different nodes where you're taking voltages from, and the paths are where the current can flow through. You can also do this, let's say these are different pipe locations with water. This has a bunch of different applications. If you remember in class, we did the little path of Winnie the Pooh that you can do with this as well. And you can create from these circuit systems what's called an incidence matrix that essentially just describes what is going in and out of each path. So as you can see right here on the top, our columns are going to be the different nodes, the different places we're measuring like our voltage from. Meanwhile, over here, our rows are the different paths that we can take. So when you set this up, we just write our nodes and we write the different types of nodes. So in this example right here, we have 4 different nodes, x1, 2, 3, and 4. And then we look at the different paths. And we can see from this image right here that we have 5 different paths. And then we close off our matrix. And all we need to do is either you can look at the nodes or look at it from the paths. I like to look at it from the paths. So for example, you can't really see, but this path right here that I started turning white, it leaves node 1. So we're going to put a -1 right there. And it enters node 2. So we're going to put a +1 right there. What it leaves from, you put a negative. What it enters into, you put a positive. And since it doesn't touch node 3 or 4, we just put zeros there. Similarly for path 2, which goes from 1 to 3, we put a -1 on 1, a 1 on 3, and zeros everywhere else. For path 3, it goes from node 2 to node 3. So again, -1, 1, zeros in the other spots. Path 4 goes from node 1 and goes into node 4. And finally, path 5 goes from node 2 and into node 4. And just like that, we've set up this same incidence matrix that you see in the image right there. Does setting up an incidence matrix make sense? Any questions about it? Cool.
So for W4, we have X1.
W4. Yep, it's leaving X1. Yep. And so your homework, it only has this type of image, but if you were given a different type of circuit system with the nodes and paths labeled, do you feel confident you'd be able to create the matrix? Okay, cool. In addition to that, we can use Kirchhoff's voltage law, and we can multiply our incidence matrix by a vector V, which represents each of the voltages, so we can find the voltage differences between the different nodes, which is right here. And as you can see, we just create a vector V that has the appropriate size to be multiplied by A, and then you get the voltage differences. Yes, we have 4 voltages because we have 4 nodes. If we had 6 nodes, we would have a V5 and a V6 on here as well. Yes. Does that make sense? Real quick, there's one other question that's not in this slide that was on your application, and it asks about A transpose W equals 0. What vector subspace is that? Left null space, because it's A transpose times W. And does anyone remember what the dimensions of that vector subspace give you? The number of unique loops. Yes, because when you do take A transpose, you're then, because originally it was nodes or your columns and paths are over here. So when you take the transpose, you get paths as your column and nodes on the left. And so you're then summing up your paths. And when you do that, you're able to find the number of unique paths. Does that make sense? Yes, the dimensionality of your left null space gives you the number of unique paths, yes. Okay, cool. Any final questions about circuits? Just because when we multiply this column, by this, we get V2 minus V1. Yep. Any other questions about that? Cool. That's essentially all there is to circuits. So now let's get to everyone's favorite topic of SVDs. Okay, so usually when you are going to calculate the SVD of a matrix, because you have to take a square root, you end up with some not fun numbers. So usually in these problems, we are given the SVD of a matrix. And it similarly to diagonalization, when we express our rank 1 matrices, we can determine the rank 1 matrix from an SVD as well. You use the same process. The 2 ways of doing it is you can either just go ahead and take your dominant singular value, multiply it by the first column of your U matrix and the first row of your V transpose. Additionally, if you don't want to do that, what you can do is just make the other singular value 0 and multiply the 3 matrices out, and you'll get the same thing either way. I kind of like using this method just because then I don't have to multiply full matrices with each other. So when we do this, we would have our 5 square root of 6 times our first column of U, which is root 2 over 2, and minus root 2 over 2, multiplied by our first row of V transpose, which is root 6 over 6, root 6 over 6. And sometimes it writes them like root 3 times root 2. That's the same thing as root 6. So I'm just going to write root 6 over 3. That's how he has it written in the homeworks. So because all of these are root 6 and my singular value has a root 6, and since it's a scalar, it doesn't matter which one I multiply it to first. So I'm going to go ahead and multiply this with my rows. Yep. So then 5 root 6 times root 6 is 6 divided by, or 5 times 6 divided by 6. So we're just left with the 5, and then 5/3. No, that's wrong. That's 30. That's going to be 10. Yes. Does that make sense? All right. Now all we need to do is multiply these. We have a 2 by 1 times a 1 by 3. So we're going to get a 2 by 3 out. So we're going to get 5 root 2 over 2, 5 root 2 over 2, 5 root 2, minus 5 root 2 over 2, minus 5 root 2 over 2, minus 5 root 2. There's our rank 1 matrix based off our dominant singular value. That's it. Make sense? And just kind of a mental check. Is this matrix singular? Yep, the second row is just negative times the first row. So we only have one pivot. So that checks out. Also, it is the same dimension as our sigma matrix up here, which is also good news. It should always match up with that matrix size.
So all of the
Yes. Yep. All right, they went through the work for it. All right, next one. Consider this matrix, which SVD includes U, sigma, and V. Notice that it says V and not V transpose. So with SVD, when we do this, our singular values can tell us the amount of information contained in each rank 1 matrix. So for example, it's showing right here that our first singular value contains 37.7% of our data. And it asks us for how much, for the sum of rank 1 matrices that contains at least 75% of the data. So very first thing is we need to determine how many of our pieces require. So first, we already know that it's not just the first one, because that's not greater than 75. So let's check the second one along with the first one. And that gets us 17.04 plus 14.48, which is 31.52 divided by 45.25, which is 69.66%. So now let's check our first 3. And we get 31.52 plus, what's the next one? 11.85. We get 43.37. I think this one will do it.
Yeah, there's 17.04 and then there's a 17.4. Is that?
Oh yeah, that's a typo. Yeah. And when we do that, we get 95.85%. Yippee. That means no. It wants us to find, so it says, what is the combination of rank 1 matrices that contain at least 75% of the data? So we've now determined how many of our singular values will give us 75% of the data or more, but we now need to find the rank 1 matrix. So again, there's two ways of doing it. You can do sigma 1, U1, V1 transpose plus sigma 2, U2, V2 transpose plus sigma 3, U3, V3 transpose. That's going to be a lot. So in this case, the other method might be better. If I can erase all this, which is where we just are going to ignore that one, make it a 0. So we're just going to multiply our matrices U, and then from up there and from up here. And then we're going to do 17.04, 14.48, 11.85, 0, and fill these out with zeros. Lots of zeros. Even more zeros. Times V transpose. And that will give us the sum of the rank 1 matrices. Now, these numbers are a little bit gross, and I don't want to take the time putting that into our calculator. So here we see those three make it up. And when we multiply them out, went too far, we get this matrix. That is the sum. Here, I'll write just R1 plus R2 plus R3. That was ugly. Yep. Yep. It wanted us to find the sum of those rank 1 matrices. Yep. Yeah. And it might ask for, like, originally it might give you the full matrix, but it might say instead of 8.62 right there, it might have an X right there. And I'll ask you what X is. So you could do that as well. Yes. Yeah. What it looks like is when they did this, they didn't transpose V. As you can see, these two are equal, but this is supposed to be V transpose right here. So don't make the same mistake as the slides. Transpose your V. I think there's so much information in this problem. It's very easy to just kind of glance over that V and think it's the V transpose. Is it? Oh, they did transpose it. I lied then. Yes. They do transpose it right here. That is V transpose. That's right. I'm not sure what that error is then, but yeah. Yeah. Makes sense. Any questions about this type of problem? We good? Okay. There is one other type of SVD problem in your homework, which asks you to project a few matrices down onto your dominant eigenvector or singular value vector and determine which one is closest to our control matrix, O. This is like in class when Dr. Hevlin, put up the facial recognition photos of like Wonder Woman and Voldemort and Superman and Iron Man and was trying to determine which one looked the closest. This time we're just using actual matrices. So all you need to do is first you need to turn all of these matrices into column vectors. And the way that we do that is we start in the top left, then we go to the one underneath it, then we go to the next top and go to the one underneath it. So for example, A would be -5, 1, -1, -8. B is 1, 2, 3, -2. C is 2, 3, 10, -10. And D is 3, 6, -1, 5. Additionally, we want to do it to O because we want to see how they compare. So O would be 8, 9, 3, -3. Any questions about how we did that? The reason we want that is because we're just going to essentially do a dot product with each of them. And so we want it in a column vector. That way we can actually do a dot product. So then what we do is we take our dominant eigenvector, which in this case from the previous matrix was this column, and we transpose it into this. And then we multiply it by a matrix of each of those columns. So we're going to multiply this by our -5, 1, -1, -8, 1, 2, 3, -2, 2, 3, 10, -10, 3, 6, -1, 5, and our 8, 9, 3, -3. And when we do that, we're going to get scalar values for each of those. Let's see if they have them. No. So let's plug these into a calculator real quick. Yes.
Get the
It was given to us in this problem. In this problem, it was the entire U matrix was given.
you pick the U matrix and not the you don't solve
Yeah.
the whole first
Yep.
column.
All we need is that
You just-
first column. Yep. Yep.
Not include O, finding that dominant vector, right?
No, so there's a whole in determining that U matrix, there was a statistical analysis done behind the scenes that you don't have to do of our four matrices A, B, C, D. That's, remember in class, Dr. Heaven was talking about like the covariance matrix and all that stuff. This is the SVD of the covariance matrix. Yes. Yes, exactly. So we're going to multiply these. We have one column or one row, 4 columns. Give me a moment while I type this in so we can actually see an answer. Mm-hmm. Three, 6, -1, 5. Almost there. All right, and when we do it, we get values 6.94, 2.57, 12.31, -6.34, and 0.97. So this 0.97 is our O. This is A, B, C, D. So which of those matrices is closest? B. And how close is it? 1.6. And we got that by taking that value of B and subtracting our value of O. And so it is a distance of 1.6 units away. Sorry?
One transpose, how did we get it again?
We were given our U matrix, and I just took this first column and transposed it. Any final questions about that? Yes. The review from last night was recorded yesterday at 7 p.m. and uploaded this morning. So yeah, it was posted at like 11 this morning. So hopefully this one will be posted around the same time tomorrow. But yes.
This on the Canvas page or on the recitation page?
No, so this is not uploaded on Canvas at all. What you need to do is go to YouTube and search up the AMLAX YouTube channel. So just type in like USU AMLC, and then their YouTube channel will pop up and it will be in the most recent videos posted. Sorry? I think that was your recitation leader. Yes.
From our O and then do a crossfire with the so we're finding the distance between those.
No, all we're really doing is we're projecting these matrices onto the vector of U. And by projecting them onto the vector of U, we're just able to look at their locations distance from each other along the vector U, and that tells us which one's closest.
So basically make one of these column vectors and like smush them all together.
Yep.
Then we multiply our new matrix that we just made by.
Can everyone settle down, please? Yes, thank you.
We multiply this new matrix by U transpose.
Yep.
And then that spits out.
Yep. Yep. Scalar numbers. Yep. All we're taking is the first column of U, not the entire matrix U. Yes. Because it corresponds to our dominant singular value. So it's the most accurate, contains the most information of our data. Yes. That's a good question. I just, because the U matrix is what projects it, I guess. That one I'm a little unclear about, but yes. Sorry, can everyone settle down just a little bit again? Thank you. Yes, yes. So it's that first column of U transposed times every single one of them. Yep. All right. Yes.
Can you get your final matrix? What are you comparing it to find correctness? Are you looking back at against those?
So all we're doing is when we multiply it out, we get these scalar values. And if you set it up so that your matrix is column A, column B, column C, column D, and column O, then you'll get their scalar values in the same positions. And so you just need to compare each of these first four to the last one. And whichever one's closest to that last one is going to be your answer. Cool? Any final questions? Yes. Okay. Yes. 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 So if you were to do U1 and U2, then you would get 2 points for each matrix. And instead of plotting it on a number line, like A, B, O, C, D, like that, you'd have a plane in direction U1 and direction U2, and they'd have points on there. And so then you just probably want to take the magnitudes and find the distance like that. But yeah. And then was there another question? Mm-hmm. Yeah. Let's go back real quick. Yeah, I'm not sure. Because these are gross numbers, you might not be asked a question like this. Or if you are, it will be asked in a way where you'll be able to do it. Cool? Any final